Good morning, everyone, and welcome to session 104 of the EDP and Applied Matematica seminar. Today we have two excellent speakers, Sebastian Zamorano from Chile and Maria Lopez from Spain. It's an honor for me to introduce to Professor Sebastian Zamorano, professor from Universidade do Deusto, Bilbao, España. On this occasion, Professor Sebastian Zamorano will give the lecture entitled Tracking Controllability for Finite-Dimensional Linear System. Welcome, Professor Sebastian Zamorano, and you can start.
Thank you so much, Juan, for the nice introduction. First of all, I would like to say congrats to the organizer of this seminar for the 100th session done at the beginning of this month. So I attended to a few of them. Was very nice, and congrats, because it's not too easy to maintain this kind of seminar with 100 sessions. So congrats for you, for the organizer. So as Juan has said, I want to talk about one of my last words about the tracking controllability for final dimensional linear system. Okay, this is a young work with Enrique Suazua from the Friedrich Alexander Universität in Erlangen, Nuremberg. And also, so this work was part of my Humboldt fellowship that in the last year, I spent one academic year in Erlangen with Enrique and his group. And this is one of the result of this, the fellowship for the Humboldt in Erlangen. Okay, so the plan of the talk is these 5 subjects. The first one, a little introduction about the subject, about the tracking controllability, because it's, in some sense, I think that everybody know this kind of control property. Then the part 2 and 3, I will give you some preliminary result about tracking controllability. About the first one will be the classical Gramian operator, the Hume method for obtaining the controllability using the joint method, and so on. Then a particular case in the subject 3 about the scalar control case, and then some numerical example to show that our results are good in some sense, and then the wave equation and the semi-discrete wave equation. So because here we have a big difference with respect to the classical controllability for wave and semi-discrete wave equation. So for that reason, I want to talk about this subject. Okay. So the introduction, very easy. We have in the title I wrote tracking controllability for finite dimensional linear systems. So here a classical finite dimensional linear system. You have an ODE with A and B 2 matrices. Obviously, we have U the control and X then represent the state. Obviously, we want less control than state. So for that reason, we put M less or equal than N. And the X0, the initial condition, as always. And we know, I think, everyone here, that the classical controllability definition, that in finite dimension, we have 3 in general, but all are equivalent. But the classical one is the state controllability, that you give to the system some initial data, some final state, X1, and you want to find a control, an external control, such that the solution of your system at time capital T reach the state that you give at the beginning. Yes? So this is the condition at the X at time capital T is equal to X1. Okay? So this is the classical exact controllability. And we know also this is a classical result by Kalman in the 60s, that this property, you can represent the existence of this control such that the solution at capital T is equal to a given state. And you can represent this by the rank of this matrix, this extended matrix. Yes? So this is a classical result from control theory. But for us, we want something similar. It's not the same, the definition that I will give you, but it's in the same spirit, okay? So we call it tracking controllability. And what is the definition of this? The most important thing is here in red, so that you want to find some control as the state controllability, such that the solution of your system also reach some state, but now is a function, this f of t, but maybe you don't want to control all the state, maybe only a projection of this state, maybe one component, two component, the average of the component, or I don't know, whatever you want, okay? So this is the operator of the matrix here, E. So you want to find a control in order that your solution of your system reach for every t, for every time in your time horizon, 0 capital T, some given function f, okay? So some of you maybe can think that this is equivalent or similar to the controllability to trajectories, but it's not the same, because in that case, when you have controllability to trajectories, this f is a given trajectory that is solution to your problem, okay? It's a given solution for the same system. So here, no, you give me a function f, whatever you want. Obviously, you need some regularity. Here we put h1, and I will explain why we need this h1 regularity for the function. But it's any given function f. And you want to find the control such that the projection of your solution, some component, sum of your component, whatever you want, is equal to this function f, okay? So this is the tracking controllability. So some preliminary remarks about the definition. As I said, this is not the same that the exact controllability of trajectories. It's different. It's also different to the classical state to output controllability condition that is related with your system, the same system. You have a control in the right-hand side, and then you have this output. Yeah? Y is equal to Cx plus du, okay? And for the state to output controllability, also you want to find a control such that this output is equal to a given state, but also capital T, a time capital T, yeah? So it's different. Now we want the same, but in a whole interval of time, okay? So between 0 and capital T. So it's not in a given state and a given time. So this is given by the result of Bertrand and Sarachik in the 60 also. Some other remarks about the regularity, because this is very strange, because in general, when we analyze the controllability in final dimension, you know that control is in L2, the function is continuous, blah, blah, but you are in Rn, okay? So your state, your x1 state, that the state that you want to reach, is a given state in Rn. So you don't need to put any regularity in the final in the final state. But here we need to impose this regularity for the function f, and this is obvious in our case. Why? Because you know that if you have a control in L2 on the right hand side, then your solution implies immediately that you have a solution in h1 in time. So at least you need that the projection of your state of df that you want to take need to in h1, okay? So, but here, maybe this is the started point with Enrique when we start to analyze this problematic, that, okay, we know also the Brunowski canonical form for final dimensional system. We say, okay, we can use Brunowski canonical form, but I will show you that with this canonical form of Brunowski, the H1 regularity is not enough in some cases. So you need more regularity for your function f. So this is very strange. For me and for Enrique was very strange. And for that reason, we start to analyze this tracking controllability for finite dimensional system, because even in finite dimension, you have a big difference with respect to the previous controllability result. So here it's obvious that the system is linear, so you can consider that your initial state is 0. So, but in that case, you need to add this extra compatibility condition. So this is obvious for our system. So another remark, in our case, now we can define this control to output state, but here we have a very big difference with respect to the previous notion of state controllability. So now you have your control in L2. Now you want to find this control in order to reach a function in H1. So then you have this operator, the classical operator. But now you go from L2 to H1. But for state controllability, the classical exact controllability for linear system, you also go from L2, but to Rn. So this is a very big difference, very big difference with respect to the previous controllability properties for finite dimensional system. Okay. So this little, but at the same time, big difference, which was the starting point for Enrique and me to study this property. Okay. So our first result. So as we define this state to output or the control to output control operator, the classical properties for finite dimensional system using Kalman condition or Gramian operator and all of this the stuff, very well known result, we can prove this first theorem about the tracking controllability. And the first one is, if you want to prove the tracking controllability, you need to prove that this now the control to output, but it's not the output, it's like it's a control to track control is subjective. This is the classical one, but now with an extra or another space here that change everything in the proof. And also you can prove that also is equivalent that the adjoint operator now from H-1 to L2, and you can compute that join in an easy way. These operators satisfy this inequality, okay? So in the classical state controllability, you know that this adjoint operator is better than this. Why? Because here in red, you don't have H-1, you have Rn. So this is very important, okay? So also the proof here, you need to change a little bit. And also you have the tracking Gramian operator. We define this operator given by this. So now you have from H-1 to H01 and defined by this integral, and you need to prove that this operator is invertible, okay? Here, this H01, meaning the meaning of this is that in time 0, the function is 0, okay? Because we need this extra compatibility condition in the function f, that in 0 is equal to 0, so we define this space A01 as I say, okay? So this theorem, the proof is very similar that for the classical state controllability, with the obvious difference with respect to the state, and with the difference with respect also with this space, H-1, H01, that's a little different, but at the same time, a big difference, okay? So then we move on, and also we analyze the Hume method, yes, the Hilbert uniqueness method. So for this, we know that we need to introduce the joint system, but here also we have a difference with respect to the previous classical exact controllability for linear system or for finite dimensional linear system. Here we need to consider this function g in h minus 1, okay? And you need to consider this adjoint system. That is very different with respect to the well-known result about the exact controllability for linear system, no? For finite dimensional linear system, okay? So here, maybe some of you can realize that this is more related with a tracking optimal control problem, yes? Because here you obtain a right-hand side in your adjoint problem, yes? As a source term. So this was one of the motivation also for studying this tracking controllability because of this adjoint problem, because it's related with this optimal control problem of tracking type. With Enrique, we worked a lot on the tarpal property. So the tarpal property, optimal control problem, and related with this adjoint problem, and then we start to study the tracking control property, okay? So here we have a source term here in h minus 1. So you need to define the solution of this system too, the joint system, with obviously with by transposition or a weak formulation for the solution, because you don't have enough regularity. So this is the definition of the solution, classical way. And then we introduce the obvious generalization of the classical observability inequality and now the tracking observability inequality. Yeah. So here you have G, but here the norm is very strange in h minus 1, and you need to prove this inequality. Yeah, this is the tracking observability inequality for your adjoint system. So let me move on. So we prove this theorem. This is the classical Hume methodology to prove it. So I will skip the proof because it's not important. But the most important thing that you have F in H01, and then for every F in H01, your system is tracking controllable. Obviously, if the adjoint system is tracking observable. But some remark about this, a very important remark that we know for the final dimensional system, that is, in your final dimensional system, if you have the observability inequality, you can prove also the approximate controllability result, using that in Rn, in a final dimensional space, all the norms are equivalent. But in this case, we are working in a finite dimensional system, but your control property move to a space that is infinite dimensional space. So here, we don't have the classical equivalence between exact controllability and approximate controllability, or the exact controllability equivalent to a unique continuation property for your adjoint system, okay? So this is a very big difference with respect to the classical well-known result for finite dimensional system. So for that reason, we study also the approximate tracking controllability, and it's the same that in the classical finite dimensional system. But now we can reduce the regularity for the function f, yeah, because we are in the approximate case. So we can reduce f to L2, and then we can prove this inequality for the controllability. Okay, so this is our third theorem with Enrique, and was that the adjoint system satisfies the unique continuation property. Okay, and this is equivalent to the approximate tracking controllability. So at the end, we obtain all the same result that you have for final dimensional system, but with a little, but at the same time, big difference with respect to the space. Okay, so it's very, very clever, or at least for me, this small but big difference. Okay, so then we study a particular case that is the scalar control case. So we consider only one control. Okay, you don't have M control, only one control. So you want to control one equation or put a control in one equation, and you want to control all the state, all these n-1 equation. Yes? So some preliminaries about this. This is the classical definition of similar control system. I will skip this, but the most important thing is the Brunowski result about when two systems are similar, or when you have a system that is controllable in the sense of Kalman, or the classical exact controllability, then you can obtain a similar system. Okay, that is very, very, very important. So this is the Brunowski result from the 70s. And okay, if you have a system that is controllable, the condition that you need only one control is not in the result of Brunowski, but here I put this result because it's easier to do the computation. So then you can obtain two matrices, A tilde and B tilde. A tilde given by this matrix, and B is, where is B? Here is B. B tilde is this one, the canonical vector in Rn. And then, okay, and also you have obtained a similar system for your original AB system, okay? And also you have the conversely. So if you have a matrix P that's invertible, such that you can write your matrix A in that way and B in that way, then your system is controllable, okay? So this is very nice, very, very nice, because this matrix, very important, yes? Because you can in some sense, trespass the information of one equation to another one, to another one, to another one, and then at the end, you need to control. Okay, this is the main idea of this. Yeah. So using the Brunowski canonical form, we prove this fourth theorem with Enrique, and it's the following one. You have your final dimensional system with one control only, and you assume that your system is controllable, okay? In the classical way. So what is the meaning of that? You have given a state, x1 in Rn, you can find a control such that the solution of your system at time capital T is equal to x1, okay? Assuming that, we can prove that also your system is tracking controllable. But in this case, we need to assume this regularity for your target. And this is very strange, okay? And in the proof of the theorem, you can say why we need this number star. That is very strange, but in the proof you can see that. But for us was, okay, you have a system that is exact controllable, and then when you want to analyze the tracking controllability, it's very strange. So you need more regularity, less regularity in DF, so it's very strange, okay? And also you can generalize this theorem to the case of AB with B matrices, with A and B matrices, but the notation is I think that the result is not better than this, okay? It's only the notation increase the number of components and blah blah. So it's not needed to do that. Okay, I don't know if I have enough time, but some numerical example for our tracking controllability. So the most important thing is that, okay, we know Hume, so we know also the penalized Hume method in order to compute numerically a control. So here we made the same. So we consider a function, a functional g. You have this, you need to minimize the control u, but here you need to penalize your state, but in the whole time interval. That is very different with respect to the classical controllability. Okay, so it's very different. So the people that work in optimal control problem, this is a classical optimal control problem of tracking type. Okay, for that reason we call it also tracking control. Okay, so okay, so here is the difference that I told you, that I said before. And now, so we consider this very easy finite dimensional linear system. We put capital T, the time capital T equal to 10. And then using Casadi, this is an open source tool for nonlinear optimization problem. We solve this optimization problem and we obtain this result. For instance, if we consider first to project the first component of your solution, and let me go back one slide here, we put the control in the second state, in the second equation. So if you want to only look the first component of your state, and you put this f, a very regular function f, you obtain this result. So you have your f, and you can see that the x1, the first component of your solution, track very well your solution. Okay, and the control, in some sense, is similar to the classical controllability. When you look at the control at the beginning, start, move your solution from the zero state, the classical move, then stop to work, and then say, okay, say the solution need to evolve alone without control. But here you need an evolution of your control in some sense. It's not a stationary. Okay. And then also at the end, again, the control acts in a maybe in a high amplitude with respect to this whole time interval. Okay. In the case when you want to see the second component, it's better because your control is in the second component. So now it's better. But here you can see that the control is like a periodic function. It's like the sign function. So it's different with respect to the classical exact controllability. Okay. So here, the last numerical example, we put a very irregular function. Okay. And then here you can see that also the function, the state follow in some sense in a very good, or maybe not so good, but similar track this function f, and your control is very, very strange. Yes. So this was for us very important result because give us an intuition that, oh, maybe it's important to analyze this tracking controllability for finite dimensional systems. Okay. So then we analyze the heat equation with interior control, with a source control, and we say, okay, I want to see if the normal derivative of the end of the interval in x equal to 1, we want that this normal derivative is equal to a given trajectory f. So it's very different with respect to the classical control problem. So here we put this F, and the result, okay, we use again Casadi this open source tool. Here, all the classical definition of the spatial point, your mesh, and blah, blah, blah. So then we obtain this result, very nice. Let's say, okay, classical heat equation, very nice, linear with control in the right-hand side. So it's perfect. The behavior of this heat equation is like a linear system. So this result is some sense expected, okay? But let me finish with the wave equation. So this is very, very, for me, was very important example. So wave equation in 1D, okay? But linear wave equation with a control in the boundary, okay? On the boundary. So in the left-hand side of your interval, okay? And also, as the heat equation, we want to find that the normal derivative of your solution and in the other side of the interval reach some given function f, okay? So you want to control in the left-hand side, and then you want to see if in the right-hand side, the normal derivative is equal to some function f, but in all the time interval, okay? Different with respect to the classical control. So a nice result of Enrique and the Simsarag in the 2022 is about that, okay, for your wave equation, linear wave equation in 1D with control at the boundary, and you want to track the normal derivative of function f, you obtain very important result and different with respect to the classical result for the wave equation. You need a time, obviously, because you need the propagation of the energy of your solution. But also you need to consider a function Q very regular, very regular. Your control function is also very regular, C2. And also, well, obviously your solution is also very regular, is C2. And then you can obtain that the solution of your wave equation satisfies that the normal derivative in the left-hand side is equal to your given function Q, okay? The proof of this is very nice, but it's different, or it's only you can do this proof in 1D, okay? And was very, very important because when we started this the study of this tracking control for finite dimensional system, we say, okay, we know that for the wave equation you have the tracking control. So we know that the wave equation or a heat equation or a PDE, when you do the semi-discrete version, you obtain a linear system, yes, of ODE. So okay, we know that the wave equation satisfies the tracking control. So what happened with the final with the semi-discrete wave equation? So we do that. This is the semi-discrete version of the wave equation with control on the boundary. Then this is your tracking control. You need the normal derivative track some function f here in red. Then using the boundary condition that the ended point is equal to 0, you obtain that this is the mesh. You have this condition in blue. And then if you replace this term in your equation, you can obtain this. You can obtain explicitly your control. And this is very nice. And this is given by Brunowski canonical form, because it's the same. When you look your wave equation, your semi-discrete wave equation, you can see that it's a system, obviously, And this is very similar to the Brunowski canonical form. So you can obtain explicitly your control, but also you can get this, that the function f that you want to track need to be in this space. You need a lot of regularity. And because of what? Because you put your control here, you want to track a f here, and then you start to go back to your control. So you lose 2n. So you need to ensure 2m regularity for your function f. Okay. So I almost ended. So one important thing here, that in the semi-discrete setting, this tracking controllability is achieved without conditioning the time, okay? As in the for continuous wave equation, okay? Okay. So some reference here. The first one is a paper also from Enrique and Jonasier from the University of Lost Country about the tracking control for the heat equation. This is the paper of Enrique also for the 1D waves. Here our preprint, and also this Fourier series and sidewise control for 1D waves. And that is very, very, very nice, in some sense, survey about this tracking control. Okay, so thank you so much for your attention.
Thank you so much, Professor Sebastian Zamorano, for your excellent presentation. Now is time for your question. Do you have any question or commentary? Spanish, Portuguese, English?
Chilean also.
Any question? Or
Juan, just a curiosity. I wondered if you can have a similar result, not for tracking a normal derivative, but the solution. So
for wave?
But for heat or for wave, because you are always tracking normal derivatives. So I wonder if we can have the same kind of result when we put just a solution in some point.
I think for the wave, for the heat equation, they proved the tracking control for the normal derivative, because you need, in some sense, like an inverse problem. You need an extra measurement, in some sense. You have control in the Dirichlet, and then you need an extra that in this case is the normal derivative.
Yes, I imagine that, yeah.
Yes, it's similar to an inverse problem. It's very similar in that case. Yes, but it's very like you need to consider, you need to give the output. So you want to control the normal derivative, then you analyze the case. So it's only for final dimensional, for ODE, we can put a general output. Yes, your E matrices with X, but for heat and for wave, we don't know.
Okay, thank you.
More question? More question? Sebastian, is possible to tracking controllability in nonlinear problem?
I think that maybe yes, because as always you need linearize your system, then you use your result of tracking control for your linear system, and then using some fixed point argument, maybe you can obtain something for the nonlinear system. But I think that the problem at the end is your time interval, because now you want to control in a big time interval. So when you use a fixed point argument, you have a local result. So I don't know if you can obtain a general result for your tracking control problem.
In the case it's possible to extend tracking controllability to linear hierarchical control.
I don't know. I don't know, because then you have more controls. I don't know. Really, I don't know. I don't want to say yes or no.
Yes,
Okay, because I don't know. I don't want to say that, but maybe yes, maybe, because tracking controllability is related with an optimal control problem of a tracking type. So maybe yes, but I don't know, because your adjoint system is the problem. This is the big problem. So I don't know. Really, I don't know.
Thank you, Professor. Any question or commentary? Well, if there are no more questions, thank you again, Dr. Sebastian Zamorano, for your amazing talk, and see you
Thank you
in
so much.
another opportunity.